Cameron, it's 12:30. Let's go ahead and get started. If I can have your attention, please. Cameron has an announcement.
Hi. So my name is Cameron. I'm currently working on bringing the chemistry club to main campus. And so we actually had a club on main campus before, but that club became inactive about 2 years ago, I want to say. So my sister helped with co-founding that original club, but now I'm working on bringing it back. So we actually have an advisor now. We're hoping our first general meeting will be on Friday, February 22nd, 1:45 to 2:45 p.m. We're still figuring out a location, but it will probably be on main campus, second floor of Millard Hall. Some of the focuses of our club, we're going to focus on getting the community involved with getting interested in chemistry, such as doing outreach events with science centers, working with elementary schools and middle schools, doing science experiments with them. And of course, there's a lot of fun perks to being just involved with the club. We're trying to do experiments at every meeting. They'll be on the first and third Fridays of every month. Yeah, and then it's just a lot of fun. So I hope you guys can make it to our first meeting. I'm gonna write the club email down here if any of you guys need to contact me. I heard you guys also were wondering if I could put down my my phone number, which I can. Let's see, @gmail.com. Because we are still looking for officers, so if you were interested, yeah, my full name is Cameron Hakeem-Malaki, and I'm not sure if I fully remember the email, because if I don't, then you can take down my phone number and then contact me if you have any more questions. I'm going to be making a whole lot more announcements, and I'll be working on a flyer that I can send to you that will confirm what location it is when I get one.
Sounds good.
Yeah. Thank you so much for that.
Thank you, Cameron.
Yep.
Well, where were we? In lecture material, we had just finished up, I believe, the previous example, which focused on what we call the small k approximation. We said that in general, small k was when k, kc, kp was less than 10 to the minus 4 or 1.0 times 10 to the minus 4. Although we just did an example where even though kc was 1 times 10 to the minus 3, it was still considered small. That's because the true test of whether k is considered small is that the extent of reaction, or the amount of reaction, that's the part in the C column, the change column of your ice table, was less than 5% of your initial concentration. That's the true test. Any questions before we get started? If not, one of the things I promised you was at least 50 to 100 ice tables this semester, and so we've seen a couple of them already. Let's do another one. In this example, and I believe, correct me if I'm wrong, I did not start this example. Is that correct? Correct. Awesome. This one's the example called the perfect square. That was my nickname in high school. The value of Kc for the following reaction is 57 at 700 Kelvin. Determine the equilibrium concentrations if 1 mole of hydrogen is allowed to react with 1 mole of iodine in a 10-liter container. We didn't give you concentrations, but clearly we gave you enough information to find the initial concentrations this time. And determine the equilibrium concentrations given a value of K, in this case Kc. If you're reading along and you want to figure out what type of problem, those are hints that this is going to be an ice table problem in which that ice table includes x's that you're solving for. If you don't know, just keep going and see what happens, because chances are on exam 1 that the chapter 15 material will involve an ice table. I mean, there's going to be several of them. This is going to be a molarity ice table. We're working in terms of Kc, which is concentrations in terms of molarity. I'll write my reaction out. we have our initial concentrations, 1 mole per 10 liters, that's 0.100. And we may assume, since it does not mention it, that we're starting with no products. Good assumption. That means that if we were to calculate a QC, remember QC is initial concentrations, not necessarily at equilibrium. That is the same expression. It's going to be products over reactants. If our numerator is 0, QC is 0. QC will be less than KC, and that is a sign that we have to proceed to the right and make new products, which, of course, because we have no products, that's true, but it's nice to check in with that and think about which direction we should be going. Any questions about what I just said? Clearly, if we have no products, we have to go to the right to get to equilibrium. Where is the position of equilibrium, if I may ask? Is it far towards products, far towards reactants, or somewhere in the middle, based on the value of Kc? Somewhere in the middle. All right, so we know a lot about this already. Now let's solve it and make sure our answer makes sense. Coefficients are 1 here, so we got just minus x for each of these. We have plus 2x. As a reminder, the C column, the change, always involves the coefficients. I will write out my Kc expression as products raised to coefficients over reactants. And then I'll plug in terms. We have the equilibrium quantity here, 2x, and that is quantity squared on the top. So we have 2 places where the coefficient shows up. We have each of our reactants showing up on the bottom, and lo and behold, we have something squared on the top. We have the same thing on the bottom, so something squared on the bottom. Now what we're going to do, and I'll write it out again on this page. As the perfect square so that you can see it, I'll set it equal to 57.0. And then we will square root each side. Hence, getting rid of having to solve the quadratic smiley face. I get, for the square root of 57, 7.55. Cross multiply, what have you, get terms on the same side. I will leave the algebra for you to do, but I will tell you the right answer. X equals 0.0791. Molarity. Do we have to check in with whether this is less than 5% of, like when we do small k value approximations? The answer is no, because there were no approximations made in solving this problem. So we're done. And we would expect, what's nice about this is, this works whether k is small or not, because again, it is not an approximation. And in fact, it's 79% of our initial concentration. Now, I will always ask this. You can always bet that you do need to calculate the equilibrium concentrations. Those are going to be 2x for the hydrogen iodide. Which, oddly enough, I don't have on my paper. 0.021 molarity, if I did my math correctly. Questions about that?
Can you
Kenneth?
repeat why we don't have to check to be sure? It's-
Good question. So the question was why I don't have to check. So this is an example in which you have a perfect square. On the previous example, we assumed that k was small and that the x value was much less than 0.1, the initial concentration. And therefore, we assumed that x was 0 in part of the calculation, and x is not 0. So we just had to check to make sure it was a small percent, less than 5%.
Okay.
In this one, we mathematically took the square root of both sides, but there was no approximation.
So it'll explicitly say, assume that you can ignore x or something like that.
Great question. When you come to the exam or the homework, will it say, you can assume that you can ignore x? Never. You have to know when you can ignore x. So, that's why we lay out specific criteria that says if k, kc, kp, one of the many k's we're going to see coming up, is less than 1 times 10 to the minus 4, you're good. If it's greater than that, you still might be able to do it better, but check it at the end. Yeah, and I guess the take-home answer is always check at the end to be 100% sure.
Okay.
Any other questions? Cool. All right. So you're going to do a lot of ice tables for the homework. That's the quantitative nature of studying equilibria. We will do, and it applies to a bunch of the other chapters as well. Now it's time to get qualitative. Qualitative means without numbers. And when we talk about equilibria and being qualitative about equilibria, we're really talking about Le Chatelier's principle, spelled Le Chateliers, but pronounced typically Le Chatelier's. Definition: if a stress is applied to a reaction mixture at equilibrium, so that is definitely important, you are at equilibrium, and the reaction is stressed, that's going to mean something has changed about the reaction. And then we're going to want to understand how the reaction responds. A shift in the position of the equilibrium occurs in the direction that relieves the stress. And we'll use the term stress or change to a reaction at equilibrium. And the key thing to remember is when a reaction is at equilibrium and then it's somehow moved away or stressed, it will always go back to equilibrium. Because equilibrium is the lowest energy state, good word, for the system, which is the reaction. So it's the lowest energy state for the reaction. Stresses that alter the composition of a reaction mixture, changes in concentration of reactants or products, changes in concentrations of reactants or products for aqueous species, and I should add, or gaseous species. The key thing being that solids and liquids are not here because solids and liquids do not appear in equilibrium constant expressions. They don't have concentrations really that change. For blank, for gases, changes in pressure or volume. And what we will see is that typically, if a reaction is at equilibrium, we can't typically change the pressure unless we change the volume. Changing the volume will change the pressure. So they go together. Typically, it's just easier to physically change the volume and then watch the pressure respond. Number 3, add heat or change temperature for exothermic or endothermic reactions. Add heat / change temperature. Change T, that's capital T for temperature. And what will happen is we will give you a variety of conditions. These are the ones that are going to affect the position of equilibrium. In a few minutes, we'll talk about some that don't affect the position of equilibrium to keep all our bases covered. One thing I'll talk about in a few minutes, or later in the lecture at least, is that catalysts do not change the position of equilibrium. Now we'll talk about that more. So now that we have a summary, let's go through how this works. So changes in concentration, the stress or the change, added reactant or product is relieved. That stress is relieved by the reaction shifting in the direction that consumes the added substance. And here's how I understand this, and this is sort of my system. Any system works. I think of equilibrium as the reaction is on a balanced seesaw. And it's not an English class. I don't think there's a hyphen in seesaw. I think it's just see-saw. But I could be wrong about that. All right, and so let me draw my balanced seesaw. And the balance point of the fulcrum is underneath the 2 arrows. Okay? And we will add a reactant. And this time we'll just add A. And we'll talk about how to add A. But for now we'll add A. And so I have more A, which weighs down the seesaw on the reactant side. So the seesaw now looks like that. And it is not at equilibrium anymore. To get back to equilibrium, you have to take some of the reactants and shift them to products. That will rebalance the equilibrium. So turn some reactants into products. To reestablish equilibrium. And that's the long way of saying it. So add reactant. The reaction shifts to the right, towards products. So on a quiz or on an exam, don't even know if there's going to be quizzes, on the exam, if the question will say, when something happens to a reaction at equilibrium, does the reaction shift right, shift left, or no change? When you write shift right, that is equivalent to saying turn some reactants into products to reestablish equilibrium. And if you on your exam feel better writing this version, that's fine. But you could also just write shift right. Shift right is shorthand for that whole sentence right there, or phrase. Question?
Why doesn't adding reactants induce no product?
Question, why does or doesn't.
If you're adding more, say if we add more reactant, then we're going to have to create more product to get back to equilibrium, but wouldn't adding more reactant create more product?
We're at equilibrium. And now let's touch base with some numbers here. I like numbers, maybe you do too, but I think there's a no number version of how to do this, and then there's a number version. So let's start with equilibrium. And what we said in last lecture was that QC equals KC, and that both of them have the same expression. Like that. And it's a generic example, but let's assume all the coefficients are 1 for simplicity. And then we add A. So the concentration of A is now greater. What can we say about QC in its relationship to Kc? Will QC be greater than, less than, or equal to Kc? If these three numbers are staying the same, and this one is getting bigger, QC will be smaller. And in order to get back to Kc being equal to, or QC equal to Kc, sum of A and B will have to turn into products. So this is a very prescribed situation, which is the reaction is at equilibrium. We change something. How is the reaction going to respond? And our answer is we add A to get back to equilibrium. And it's the same thing that QC tells us. To get back to equilibrium, sum of A will react away, some of B will react away, and some of C and D will be made. So yes, more D and more products will be made when we add A. And this is our system for understanding it. I don't know if that addresses your question.
I guess I just don't really understand, like, so we added A, so the question is, how do we get it back to equilibrium?
How do we get it back to equilibrium?
And then sort of wouldn't we just, in order to create more product, don't we need to add more reactant?
Let's see. So, the only thing, so how do we get it back to equilibrium? If the reaction is doing it. Like, we can't add anything else. We've done one thing, and isn't it enough to ask us to do one thing well? Right? Now the reaction is going to do one thing well, which is balance itself back to equilibrium. And so, maybe this is the breakdown, and I apologize for this. We do something to the reaction, and we're waiting for the reaction to get back to equilibrium. So we can't add D to get to equilibrium. That would be two things we're changing. Maybe that? Yeah. So this is, how does the reaction responds by turning some reactants into products to reestablish equilibrium. So this is just the reaction doing its thing. And just like, and we've been doing that already, because ice tables say, I don't care what we start with, if we know the K value, we can figure out how the reaction will go to get to equilibrium. So maybe we're getting it. It's a process. Any other questions? All right. Well, if not, then now let's add some products. If we add some products, let's add D. Then we're going to have the product portion of the seesaw weighed down. And the reaction shifts towards reactants to reestablish equilibrium. I'll write shift left, which is shorthand for the reaction turns products into reactants to reestablish equilibrium. the reaction turns products into reactants to reestablish equilibrium. Yeah.
So KC never changes, right? KC remains the same. And in order to get KC the same, that process.
So Kc never changes, and in order to get back to equilibrium, the concentrations have to change, yes, or their ratios. Yes. Although I will say, when we talk, it will turn out that Kc, and I've given you some of this already, and I'll give you more. Kc is always at a specific temperature, and we will see that Kc and all the Ks change when temperature changes. But yes, so these are assuming constant temperature. Good. Now, this time the stress, removed reaction or product is relieved by the reaction shifting the direction that replenishes the removed substance. So here we are at equilibrium, balanced seesaw. We remove B. Making the reactant portion lighter to get back to equilibrium. Shift left. Yes, remove reactant, remove product, same kind of thing. This time we'll remove C. Shift right, or the reaction shifts right to reestablish equilibrium.
How come that arrow is not?
Ooh, I put my arrow the wrong way here, didn't I? Is that what you?
Yes.
Thank you. Big difference. Travis?
But even though you have disturbed these reactions by removing or adding products or reactants, it will always try to go back to that equilibrium of what we're trying to figure out how long that's going to take.
Great question. So, question was, so we're at equilibrium, we change something, what are we trying to do, right?
Yeah.
And the answer is, we're trying to figure out where the position of equilibrium lies and how the reaction gets there. Now, you mentioned how long it takes. And that's where we want to be careful. Equilibrium says nothing about how long it takes. Okay? And time, it could be fast, it could be slow. I mean, the reactions that we'll do when we do our Le Chalais Principle Lab will be low activation energy reactions or no activation energy reactions. We haven't really talked about it, but a lot of ionic double replacement reactions have essentially no activation energy. They occur instantly. And so we're going to do reactions that occur instantly. It gets more complicated, of course, when there's an activation energy and you're trying to get to equilibrium. Does that answer your question? Any other questions? Well, I would like to go through a question. The question would be, how do you remove a product? Functionally. Oh, yeah. My notes, thank you. How do you remove a product? And for example, something as simple as the dissolving of sodium chloride. And let's say we want to remove a product. One way to remove a product would be to remove chloride ion by adding, say, silver nitrate. One of my favorite reactions then occurs as far as making precipitates. What would that precipitate be if you remember back to Chemistry 400? Silver chloride. Yes, one of my favorite solubility exceptions. Make silver chloride solid. When I make silver chloride solid, what happens to the concentration of chloride? There's less of it, right? Less, which means if we were at equilibrium and we decrease the concentration of chloride, what does Le Chatelier's principle say will happen to this reaction? Which way will it shift? It will shift to the right to products to make and reestablish equilibrium. That's our first example of how to remove a product. And you're right, it's complicated because now we got silver chloride in there as well. But it's a relatively simple example of how you actually remove a product and shift a reaction to the right. So let's see. Make silver chloride solid, which decreases the concentration of chloride ion and shifts the reaction to the right. Which decreases the concentration of the chloride ion I was hoping for some more space. Let's see. We're sort of still in your notes in the right order. And shifts the sodium chloride dissolving reaction to the right. And shifts the dissolving reaction of sodium chloride reaction to the right to reestablish equilibrium. That's work. To reestablish equilibrium. Question?
If the solid salt was saturated in the aqueous solution, and then we added in our silver nitrate, would the chloride ions then be able to freely dissolve off the solid form, or would the amount of sodium ions mess with that?
Good question. So your starting point for the question was if the solution is saturated, and for this reaction to be at equilibrium, it would have to be saturated. That would be the definition of equilibrium. We don't have any solids don't appear, so they would be the saturated concentrations. Then we would add the silver nitrate. It would remove some of this. It would reestablish equilibrium by making more sodiums and more chlorides. And at that new equilibrium, there would be more sodiums than chlorides, because the sodiums would just keep adding to it. Does that answer your question? Yeah.
Thank you.
And what you can see, by the way, is for each of these processes, there is an associated ice table problem that you will, at some point, most likely be doing. But what I find, and what the textbook manufacturers find, is that understanding which direction it should go then makes it much easier to think about solving the ice table. Questions about what I just said? That was a very good example. Okay. Yeah, and good news, some of these are already on your homework, of course. So you just have to find out, and that's some of the last things. So how does Le Chatelier's principle relate to QC versus KC? We sort of just covered that. It's worth covering again. Reaction at equilibrium. Remember, QC equals KC. We'll cover it a little more quickly anyway. Oh, now we have coefficients too. Our expression, products raise the coefficients. Our example, increased concentration of A. QC is less than KC. Reaction must shift some reactants to products or shift right. Reaction must shift some reactants to products or shift right to reestablish equilibrium. All right, good.
Nitrogen dioxide for every 1 of dinitrogen tetroxide.
Hold
and
on.
the system is at equal.
Let me at least erase here so we can see our pretty pictures.
Nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
That is an awesome flask, by the way, because it just shrunk. I gotta get one of those. So Le Chatelier's principle: changes in volume and pressure for reactions involving gases. This is for specifically reactions in which the number of moles of gaseous reactants does not equal moles of gaseous products. If they're equal to each other, no change in the position of equilibrium. But we've chosen an example where there's 2 moles of gas on the reactant side, there's 1 mole of gas on the product side, so it's definitely different. Change in pressure. We'll do Kp this time. Oh, and then I wrote concentrations anyway. I apologize. Like so. And of course, at equilibrium, it also equals QC. What we're going to do is if we decrease volume, we're going to be increasing the pressure. And if they're the same number of moles, if it was just one pressure over the other, then each of the pressures would increase in the same way and nothing would change. But here, whatever is increased here, that increase is squared in the denominator. We get the increase squared. I don't know why I put quotes around that. It is literally squared, so I don't know, but I felt the need to. If we were to think about Le Chalet's principle in terms of a balanced seesaw, the way that we might look at it is that the squared approach is equivalent to 2 arrows, which means that the reactant side is going to be pushed down more. Even though both are changing, I don't want us to get that wrong, both are changing, but the influence of the change is more on the reactants. Since the reactants have 2 moles of gas, that's squared. And the reaction must shift towards products to reestablish equilibrium. That's what the video or the animation showed. We converted some of the nitrogen dioxide into dinitrogen tetroxide. So with the black arrow, I'll write shift towards products to reestablish equilibrium, or reaction shifts. Towards products to reestablish equilibrium. Any questions about that? So this is our first case where we've changed more than one thing. That is possible, but then if you change more than one thing, then you just look at the bigger effect. Reaction involves no change in the number of moles of gas, no effect on composition of product mixture, no change. And I'll change that to no change in composition of equilibrium mixture. For heterogeneous equilibria, that word heterogeneous, I think I glossed over it a little bit before. Heterogeneous just means you could have solids, liquids, gases, aqueous phases all in the same reaction. Effective pressure changes on solids and liquids can be neglected. Volume is nearly independent of pressure. They don't appear in equilibrium constant expressions. Not a surprise that there's no effect here. Here's one, change in pressure due to addition of an inert gas. No change in the molar concentrations of reactants or products. Partial pressures don't change either. No change in composition of equilibrium mixture. So we're starting to see there are some cases where you change something about a reaction and nothing happens to the equilibrium composition. Any questions about this? All right.
Nitrogen.
So we've done concentration changes, we've done pressure or volume changes, now temperature changes. Changes in temperature affects exothermic or endothermic reactions. And this seems to be a common misconception. So an exothermic reaction, the whole thing is exothermic. An endothermic reaction, endothermic at all temperatures, exothermic reactions as well. You should think of heat as a reactant for endothermic reactions. May I ask you, have we thought of heat as a reactant for endothermic reactions before? We have. As a product for exothermic reactions, and we've done that as well. And that was foreshadowing some of the events that are occurring today. 2, the Shalley's principle, add heat to an equilibrium mixture, net reaction occurs in the direction that relieves the stress of the added heat. Changes in temperature, so if equilibrium is a balanced seesaw, changes in temperature should be considered the stress on the reaction. Another way of looking at it is the changes in temperature should change the, and here is where I need my air quotes, concentration or amount of heat. Concentration, and that is true, air quotes, heat doesn't have a concentration, temperature doesn't have a concentration. Changes in temperature do not change which side of the equation the word heat ends up on. You cannot change an endothermic reaction into an exothermic one by changing the temperature. Now let's do examples. I'm not sure if any of what I just said in the past couple minutes made sense, but let's see. The reaction nitrogen plus oxygen goes to 2. Nitrogen monoxide is endothermic. In what direction will the reaction shift if the temperature is increased? What I just said. If it's endothermic, heat can be considered a reactant. If we were at equilibrium before and we raise the temperature, and raising the temperature is adding heat. In our analogy, we are adding something to the reactant side. And the reaction must shift right to get to equilibrium. And I'll be careful here. Reaction must shift right to reestablish equilibrium. Anyway, what I said on the last 2 pages, or the last 2 slides, hopefully that makes sense now. Hopefully this analogy you can start to see, and you'll have practice on the homework, works for all of the types of stresses that can be applied. Another example, the reaction given here has a negative value of delta H. Does that mean it's endothermic or exothermic? Delta H negative is exothermic. In what direction will it shift if the temperature is increased? Shift left to reestablish equilibrium. I'm a slide behind on the right there. So now we come back to our video from the very beginning of this chapter. We're not done with this chapter yet, but let's see if it makes more sense now, or we can interpret it in terms of this. It says, is the following reaction endothermic or exothermic?
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
So we apply heat, the reaction shifts to the left. Endothermic or exothermic? Exothermic. Exothermic because, as we saw, adding heat shifted it to the left. The only thing that's consistent with that is heat is a product. It is exothermic. That means that when you add heat, it shifts to the left. So I would say shifts left. Heat must be a product. Reaction is exothermic. Very good.
If a solution of lead ion,
Now, let me erase. We'll talk about what happens actually with K, the equilibrium constant. Let's take a reaction A goes to B as an example, and the reaction is exothermic. So we add heat as our product. We say we are at equilibrium. So we put it on a balanced seesaw. And then we increase T, increase temperature. Now, like we just said, when we increase temperature, it's going to shift left. Meaning more reactants. And here's our equilibrium constant expression. I guess in theory and in practice I should call that Kc since it's written in terms of concentration. And what I want to say just right here is, so we said shift left, meaning more reactants. So at higher temperature, more reactants means smaller Kc value. At higher temperature, more reactants means smaller Kc value, meaning number. And our conclusion or the thing we want to remember about this is that for exothermic reactions, K decreases as temperature increases. For exothermic reactions, K decreases as T increases temperature. These are ditto marks. For endothermic reactions, K increases as T increases. Sam, question?
Yeah, are we assuming that we can only write a reaction one way? Because I remember that we used to be able to flip the products and reactants, but now if you do that, this will be a little different, right?
Good question. So your question is about what happens if instead of doing A to B, we do B to A?
Right, and but with the heats, then it,
Then the reaction will be endothermic. And it's like you've mirrored the situation, right? Not only will your Kc value change, but this term changes,
Right.
and it all works. Does that make sense? Like it will still, like, it'll be endothermic, but now heat will be on the reactant side, and therefore you'll add heat and you'll be able to make more A, which is exactly what we're saying here.
okay.
Right? Good question, but it all works out. Yeah. There is a symmetry to this that is beautiful. In my humble opinion. Okay, well, if not, then the effect of a catalyst on the position of equilibrium. We mentioned this before, I mentioned it before. Catalyst increases the rate of a chemical reaction, provides a new lower energy pathway by lowering the activation energy. Rate of forward and reverse reactions increase. Oh, it's not a good English. Rates increase by the same factor. Does not affect the composition of the equilibrium mixture or Kc. Equilibrium is reached faster no change in position of equilibrium. And so this will be our third thing that does not change the position of equilibrium. We have adding a catalyst, we have adding an inert gas, and we have reactions for which the moles of gas on the reactant side and the moles of gas on the product side are the same. Those are the no change reactions. Now we're at the end. So we did kinetics. We're at the end of our first chapter on equilibrium, the link between chemical equilibrium and chemical kinetics. For the reaction, A plus B goes to C plus D, and we'll consider this an elementary reaction. For elementary reactions, you can write rate laws from the reactants and products. We'll do that rate of forward reaction and rate of reverse reaction. At equilibrium, rate of forward reaction equals rate of reverse reaction. And the equilibrium constant for this reaction, or based on our initial, A plus B goes to C plus D. So nothing new here, this is just Kc. But what we can do is, if we put the A and the B concentration down here on the bottom, and we put the Kr, the rate constant, down on the bottom here, we see that the equilibrium constant is equal to the ratio of the rate constants. The equilibrium constant equals the ratio of the rate constants. And relative values of the rate constant for the forward reaction and the rate constant for the reverse reaction determine the composition of the equilibrium mixture. If the forward reaction is much faster than the reverse reaction, that means that this ratio is very large and Kc is very large. Product favored. If they're about the same, the mixture is, Kc is about 1, and the mixture at equilibrium, and I'll put a colon there, approximately equal concentrations of reactants and products. Approximately equal concentrations of reactants or products. And if Kf, the rate constant for the forward, is much smaller, for number 3, Kc is very small, product favored at equilibrium. Wait a minute. Reactant favored, I apologize for that. Favored at equilibrium. C, the example, write the equilibrium constant expression and solve for the value of the constant Kc for the reaction given there. H2O goes to hydrogen ion plus hydroxide. The H2O is a liquid, so it does not appear. We only have 2 products. And now we have the ratio of their rates given here. It looks like my cursor is over. Kf over Kr. I'll write these 2 numbers out and we'll calculate our Kc value. And perhaps you will, and perhaps you will not be surprised that this ratio is 1.0 times 10 to the minus 14. (1.0 times 10 to the minus 14. Does that number look vaguely familiar? Maybe. We'll talk more about it in the upcoming times. Quick question. For the forward reaction, what order is it based on the units of the rate constant? First order. Reverse reaction? Second order. Rate constants and their units can be very helpful in determining what the order of reaction is. Subtle little hints that can give you information. And I'm just thinking of this now as I look at units, because I heart units. And I always look at them. Any questions about what we got going on here? So, and in my mind, kinetics is over here, and equilibrium, which is everything else we're doing, is over here. But every once in a while, of course, there's some tie-ins. This problem. So it says for the following reaction at 500 Kelvin, we have some equilibrium concentrations. Calculate the value of Kc. Then an additional 0.3 moles of HI with 1 liter is added at the same total volume. What concentrations will be present when the new equilibrium is reached? I'm going to leave this as a companion problem to let you practice. I do want to do one thing with it though, and that is if I'm adding products, which way is the reaction going to shift to reestablish equilibrium? The reaction is going to shift left. So for this part down here, the minus x's or the minus x term goes on the product side. Minus x term goes on product side, but this will be a companion problem. And with that, that is the end of this chapter. Done. And we still have a little over 37, 50, 10 minutes left, so let's start the next chapter. Never a dull moment. Oh, not that one. View, window, range on. Good. So that's equilibrium and equilibria in general. Now we're going to start using equilibria and apply it to acids and bases. So acid-base equilibria. We'll start by reviewing what I will call and what we did call our Arrhenius definition of an acid or base. That definition said that an acid is a substance that produces an H+, produces H+ ions in solution. And we had examples of that. And we said that HCl, well, is HCl strong acid or weak acid? It's a strong acid. Last semester, we put 100% over this. And we'll talk more about that. We also did it for acetic acid. Here's the formula we typically use for acetic acid in this class. And we said that the products were still H+, we're still an acid, it is an Arrhenius acid. The products were H+ and acetate ion, and since it was a weak acid, we defined a weak acid as an acid that broke into ions less than what percent? Less than 5%. Now this time we're in the equilibrium chapter, so we can add a little bit here to each of these. One for HCl. Does any reaction truly go 100%? No. And that was the simplification, and it does. It goes 99.999%. But the thing we're going to add here is a double arrow where the two arrows are not equal in size. That means that the position of equilibrium, and it is in equilibrium, lies far towards the products. And instead of writing less than 5%, let's see. Now we're going to say that the position of equilibrium for acetic acid lies way towards products. So updated arrows, a whole new semester. A base is a substance that produces hydroxide ions in solution. We had only a few strong bases that we really focused on last semester. One of those was sodium hydroxide, and I don't think this is how I wrote it last semester. I think I wrote it as a dissolving reaction last semester because we were focused more on that. But if we assume that sodium hydroxide dissolves and is now aqueous, well, it goes essentially 100% towards the product. But now we can do the same thing we did for hydrochloric acid. Something like that. It favors products. That's what that arrow means. No reaction is truly 100% one side or another. And at least in my class, the one weak base that you had to know was ammonia. And for ammonia, it's not exactly clear how you get a hydroxide out of that until what we do this semester. We did talk about it, and I wrote a reaction, but I sort of looked away and was like, let's not talk too much about why that happens. But now we can. And we'll come back to acids for a minute. And our new definition, called the Bronsted-Lowry definition of an acid and a base. Acid is a proton donor. And a proton is an H+. If I am a hydrogen atom that is, I have one proton and one electron. If I remove that electron, become H+, I am just a proton. In this new definition, a base will be a proton acceptor. In this new definition, and when we think of the reaction of HCl, we will add water as the solvent. In Chemistry 400, Chemistry 401, water is 99.99% of the time the solvent. Everything pretty much is aqueous. We can write the arrows as equal. We can write the arrows as unequal. I don't know. It doesn't matter to me. So I'll accept either of these answers. The key part, or not even accept just a single arrow for HCl. Those are going to make the hydronium ion, which we did introduce, although we're going to spend a lot more time with hydronium this semester, and the chloride ion. I'm going to leave that up there because we are going to do a little bit more work with it. But I want to talk about NH3 as a Bronsted base, a Bronsted-Lowry base, if you will, although Lowry tends to get the short end of the stick, and we do tend to call them Bronsted acids, unless you're English, because Lowry was English, and then I'm sure you call them Lowry. And ignore Bronsted. Now we're going to take into account that the ammonia is aqueous. We will allow water to be part of the reactants. And we get hydroxide ion. Voila! That's the reaction I wrote for NH3 last semester. But strictly speaking, it only comes out in terms of the Bronsted-Lowry definition of acids and bases. This Bronsted-Lowry definition the Bronsted-Lowry acid-base theory is a more expansive view of acids and bases. that includes all our previous knowledge of acids and bases. So as we go through this theory, if I say HCl, is that a Bronsted-Lowry or base? You can count on HCl being an acid. It may be something new in addition to that, but all the old properties still apply. So I guess that's not a period. A more expansive view of acids and bases that includes all previous acids and bases. That includes all previous acids and bases. And let's come back to this definition for a second. Acid is a proton donor, base is a proton acceptor. If I look at this reaction in terms of protons shifting and being donated and accepted, as I look at the forward reaction, hydrochloric acid is donating a proton to H2O. That's why we get H3O plus there. In this case, HCl is the acid. What may or may not be new is that under the Bronsted-Lowry definition, because water is accepting a proton, it is now a base. That's what I mean. We're going to have more expansive definitions than before. In addition to the fact that this reaction goes forward, this reaction actually goes backwards as well. Welcome to 401. Now, if we do the backwards reaction, hydronium is donating a proton to chloride, which means that the chloride ion is a base. What does the little arrow mean? The little arrow just means that in this reaction, the forward reaction occurs much more at equilibrium than the reverse. So, and the equivalent would be, last semester we said HCl breaks up into the ions chloride, and we just called it H plus last semester, but now we're going to call it hydronium. We just said that happened 100%. So these arrows mean that essentially the reaction goes 100%. What's happening in the product side? So if we think about this reaction going that way, right? This, first off, Chem 401, this reaction goes in the reverse direction as well. If we think about how hydronium changes, hydronium going to water has lost an H plus or donated that H plus. And so that's why we call it an acid. Angel?
Would also still be the conjugate to
You want to talk conjugates, don't you?
I guess.
Wait 2 or 3 slides. Or, well, probably to Wednesday. But yes, you're on the right track. There are conjugate, what we'll call conjugate pairs in there. I just want to do the ammonia over there and do a little bit more about this acid-base donation and accepting. But that is exactly where we're going.
I'll wait till Wednesday.
Thank you for being patient. Esperanza?
So you're saying it's at equilibrium, but it's also just having one part of it having more, like, longer?
Yes, so
basically the curve, like the graph, where you're usually doing the curve in little arrow form.
so let's see. So yes, so this would have the equivalent, if we just used one arrow, is we would say this reaction goes towards products. What we would now say is that this reaction has a very large equilibrium constant. Right? That's our new way of saying that this reaction favors products, has a lot more products at equilibrium. So it's like all these are reinforcing each other. And I'm sorry, we are out of time. I was counting on that clock more than my watch. We'll pick up there next time. And before you leave, I will just say that the second homework on Chapter 15 is not due this Wednesday, but it is now officially due the following Wednesday. And, well, so we have Wednesday, then this Friday is a holiday, next Monday is a holiday as well. So the last time you will see me, I guess you'll see me Wednesday, and then you will see me Tuesday in office hours before homework is due 2 Wednesdays from today. And I'll be happy to take any questions.